Hi, my name is Tim Sun Young. I'm a PhD candidate at Technion in the VC lab. And on behalf of Work Package 7, I'll report our result for Milestone 5, the internal testing and validation integration with the digital building twin platform. This report is delivered at month 33 in the project as a part of the second version of the BIM2Twin digital twin system. In Work Package 7 production planning, our main objectives are 1. To develop procedures for predicting outcomes of plan and design changes for simulation. Then 2. Developing the envisioned software according to the procedures set forth. And 3. Iteratively test the prototype software through pilot projects in the BIM2Twin consortium. In month 13, we delivered the first version of the software for Milestone 3. This was delivered as deliverable 7.6. In that deliverable, we showed a functional prototype of our software at Technology Readiness Level 4. This software has a user input interface that was built in Microsoft Excel. And then we also have a simulation engine that was implemented using the AnyLogic simulation software. In this deliverable, we've also showed preliminary designs of the recommendation dashboard and potential interactions with the digital building twin platform. If you would like to revisit that deliverable in video form, you can follow the QR code that we show here. Since then, we have developed the recommendation dashboard using Power BI. We have then validated the prototype system using real-world project data from the Suvela pilot project in Finland. We demonstrated this software to 6 project managers from France, Spain, and Finland in Milestone 4 as a part of the demonstration led by Work Package 8. In the time since that demonstration, we have also enhanced and extended the capabilities of the simulation itself to include simulation of the vertical transport agents such as hoists, elevators, and cranes, to improve the agent behavior in line with the feedback we received. And we have also invested significant development effort to fully integrate the software module with the digital building twin platform. In this section, we will provide the visualization of the software workflow in Work Package 7, and we hope to demonstrate the logical sequence of actions and interactions between the different components of the software, facilitating a better understanding of how people can use our system effectively. Let's start with an overview of the system, illustrated in a user flow diagram. Typical users of the software are project managers and site engineers. They will begin from the digital twin core dashboard developed by Work Package 2. There, the user can review the latest status of the project recorded in a digital building twin platform. Recall that the status is compiled from the information collected on site and in the supply chain by the tools built by Work Packages 3 to 6. So if the user determines a need to improve the current production plan, then they would launch the prediction and recommendation module prepared by our Work Package 7. So the user is first greeted by the input interface. Here, they can define different production system configurations or what-if scenarios for the simulation engine to run. They can change the parameters of resource allocations, production control policies, supply chain configurations, location breakdown zoning systems, and task dependency sequences. Once they define the range of parameter values needed for the scenario, the software compiles a set of alternative production plans and sends them to the simulation engine. The simulation engine runs each alternative production plan configuration 50 times. The simulation exposes this production system to different combinations of risk and uncertainty that occurs on the construction site, such as supply chain disruptions or severe weather conditions. Once the full set of alternative production plan configurations has been simulated, the modules is ready to present the result to the users. Our software analyzes the simulation results and displays them in a recommendation dashboard developed using Power BI. Here, the user can compare the predicted performance of each plan against each other. If the user finds any particular plan favorable, they can select it in the dashboard and that plan will be uploaded to the digital building twin platform as the new baseline plan. Now, let us demonstrate the software with a realistic use case with the Savella pilot project. Savella pilot project is a large-scale residential construction project in Finland. And at month 8 in the project, the interior finishing works are at their peak because of congestion of workers and material on site. The progress began to slow compared to the planned schedule. And after reviewing the status from the core BIM2Twin dashboard, the project manager decides they need to find a solution that will put the project back on track. So they initiated the Work Package 7 software. Once initiated, our software retrieves the most up-to-date project status and intent information from the BIM2Twin Thinking Graph database. This module was implemented using a combination of Python scripts and RESTful Application Programming Interface, or API for short. Here you can see the construction activity for installing the laminate flooring as it appears in the Thinking Graph database. And then here on the left-hand side is the raw data that we receive through the API. And on the right-hand side is the same data processed and stored in table form as an input for our software. After initiating the software, the project manager is now looking at the input interface. In here, they need to define one or more alternative plans that they want to explore. In the case at hand, the project manager felt most comfortable with changing the labor configurations. So for the first plan, they increased the crew size for 5 activities: electrical cabling, servicing of insulation for partition walls, the drywall installation part 1 and part 2, and also the floor screeding. These are the 5 activities that are most imminent in the next look-ahead planning phase. Next, for the second plan, the manager tried to adjust the task assignment batch size from a floor resolution to an apartment resolution, meaning that they want to assign tasks to the crew by one apartment at a time rather than one floor at a time. And after defining these 2 plan configurations, they submit them to the simulation engine for analysis. And here we want to showcase part of our agent-based simulation engine developed in AnyLogic. In our implementation, an agent is composed of 4 parts: the agent parameter, the perception variables, the behavior functions, and the agent state chart. Here we show the work crew agent. You can see the parameter variables functions on the left-hand side and the main state chart on the right-hand side. The state chart is a form of decision tree that dictates how the agent navigates through the environment and calls in behavior functions to perform action to the environment. Here you see the work crew agent going through a cycle of work. The crew first receives instruction from the supervisor, then selects a task from the assignment log, and move either to storage or to the work location. If there are material and equipment that needs to be hoisted to the location, the work crew will send a hoist request to the crane, wait for the item to arrive, then unload or install the item, and finally releasing the crane. After all that, they will start working on the remaining parts of the task. And once done, they will report back to the supervisor. Next, we're showing the hoisting agent. This is a new agent that we have programmed recently, and it covers cranes, material hoists, and elevators. For the crane, The agent goes through a cycle of receive requests from the work crew, go to the loading location, load, transport, hold for the crew to unload or install, and finally being released for the next task. Once the simulations are done, the manager can view the results in the recommendation dashboard. In the dashboard, they can see that both the alternative plans will perform better than the original plan. Comparing the two alternatives, they can see that the plan with the increased crew size, alternative plan number 1, will cost the project more but finishes faster and is less risky. The second plan, which reduces the production batch size from floor to a single apartment, doesn't add extra costs but is more risky. One can see the difference in risk in the Statistics tab of the dashboard. Here, the user can see probability distribution of project finish date and progress within the next 1, 2, and 4 months. For Plan 1, we can see that the average predicted duration is around 288 days. And from the histogram, we can see that most of the projects are predicted to finish either before or around the ballpark of the average finish date, which means that there is a high confidence interval that we will finish the project on time or around that time. Now, if we look at Plan 2, the average project finish time is 304 days, which is higher than Plan 1. And if we look at the distribution, we see that there is quite a high chance for the project to finish way past the average 304 days, signified by a long tail in the histogram. In our use case, the project manager places high priority on minimizing the risk of the project. So he decides that he would choose alternative plan 1 as the new baseline plan. So he would go to recommendation dashboard, select alternative plan 1, and then commit this plan to the digital building twin platform. When a planner selects an alternative plan, it will trigger an update function in the software. This function takes data defining the selected plan, converts it into graph format, then uses API calls to replace the original plan in the thinking platform with the new one. Here you can see a side-by-side comparison of the as-planned work crew in the old and new plan. The partition walls work crew here has increased in size from 1 worker to 2 workers in the new plan. This concludes Work Package 7's Milestone 5 deliverable. To summarize, the software has now achieved TRL Level 5. The main upgrades since the last version were enhancement to the simulation engine to incorporate vertical transport operations, the development of the recommendation dashboard, and the full integration with the digital building twin platform. So far, we have only validated our software through the Savella pilot project. This is because we need a large, high-resolution, and high-quality dataset to test the software properly. And the data collection process is both manual and time-consuming. And so far, we have only collected everything we need for the Savella project. But now we're in the process of collecting data for the Mislata and Postialchio project for the upcoming demonstration. So, in the next version, we'll focus on integrating live pilot project data to push the software to TRL Level 6. We will also work on improving and validating the performance of the predictive simulation engine. Also, in building the integration functions for the thinking graphs, we realized that the simulation output is richer than we have originally envisaged when designing the BIM2Twin ontology. As such, there is an ongoing conversation between Work Package 2 and Work Package 7 on whether the current ontology should be revised to capture richer project planning info. Lastly, we at Technion would like to thank our partners in Work Package 7, Spada, Flow Technology, and IDP for their contribution. We also want to give special thanks to Acciona and TUM for their support in the demonstration and development activities. We also want to give special thanks to Acciona and TUM for their support in the demonstration activity. And we also want to give thanks to our internal reviewers for their valuable feedback. Thank you for